Thank you, Kuyi, for the invitation. Thank you, everyone, for being here. So, yeah, I'm going to start the course today just by giving what I'm going to do, what's the plan of the course. I advertise the course with a lot of fluctuation theory, but in fact, I will develop the fluctuation theory as I will need it. So, first I will start by working on self-similar processes. So that will be lecture 1. And here I'm going to motivate that by examples. So motivation of self-similar processes via scaling limits. Okay. Then I will describe Markov self-similar processes. Okay. Then in lecture 2, I'm going to describe positive self-similar Markov processes. Okay, and its connection with Lévy processes. And here I want to ask if everybody is familiar with Lévy processes. Is there anyone that hasn't followed a course on Lévy processes? No? So I can assume everyone knows what is a Lévy process, what is its connection with infinitely divisible laws and Poisson point processes. Is that fine? If there is somebody that hasn't followed that, it's just good to know. Just I can remember that. I can make a, well, like, okay. If needed, you just ask me. Okay. Then, so I will be speaking about positive self-similar Markov processes and its connection with Lévy processes. Then, in lecture 3, I will start developing some applications of this or some consequences of this, in particular with exponential functionals of Lévy processes. Processes. So this is lecture 3. Lecture 4, what I plan to do is also to develop more properties of exponential functionals, in particular the asymptotic behavior of exponential functionals. Of Lévy processes. Okay, and here I will need some fluctuation theory for Lévy processes. So I will introduce some of these ideas, and then in lecture 5, what I plan to do is to describe entrance laws of positive self-similar Markov processes. And there we're going to see these are quite related to exponential functionals of Lévy processes. Okay? exponential. Okay. And then, starting from lecture 6, I will speak about self-similar Markov processes in RD, okay, and what is called Markov Additive Processes. Okay. Markov Additive Processes is a generalization of Lévy processes. And these are processes that have essentially the same structure as Lévy processes, but there is a main difference, which is that the jump structure depends on the environment. There is an environment that drives the process, okay? But still they have the same additive property and same property of independent increments, essentially, okay? So that makes that there is a whole theory for these processes that is parallel to the theory of Lévy processes, okay? So lectures 7 and 8 will be on the fluctuation theory of, this will be called maps, okay, of Markov additive processes, and lectures 8 will be some applications on entrance laws. Of self-similar Markov processes in RD. Okay, that's essentially the plan of the course. Okay, let's see if we can do it, because it's a lot of material. It's quite ambitious, but I'll try to not to go into too many details, but give you more ideas of the proofs of some of the results that appear here. And yeah, so in some cases we will restrict to some more simple examples, as for instance here for exponential functionals, we'll do a lot of things for exponential functionals of subordinators. Okay, and here the asymptotic behavior that we will deduce, we will mainly use the renewal theorem. Here, I think I'm going to just state some of the results, state some consequences, but not give a proper proof because they can be quite involved. And yeah, here I'm going to introduce Markov additive processes in a general setting. I will give some results in the more simple case, which is when the driving process is a Markov chain. Okay, and with that I will try to give some ideas on the fluctuation theory. And in fact, the fluctuation theory for Markov additive process, I'll try to motivate it using random walks. And yeah, and from there I'm going to explain how the fluctuation theory and some renewal theorems can be used to develop the theory of entrance laws for these processes. Okay. And what else do we need to know? We need to know that you can send me an email if you have questions, or you can ask now during the course. My email is rivero@cmat.mx. And in my web page, there are some notes that are not very easy to read because they are something like that. It's a course that I gave in a board that was translated into the PDF file. But there you can find some nodes that are closely related to this course. So that may be useful, and eventually we will type some of the nodes of the course. Okay. Well. Okay. So let me start with the motivation. Of as scaling limits. Okay. The study of scaling limits is something that has been there since the beginning of the times for stochastic processes, and I think one of the basic theorems is Donskoy's theorem. And most of these scaling limits started to appear in the literature about stochastic processes in the 50s to 60s, but still nowadays they are always studied. Okay, so what do we know by Donskoy's theorem? Donskoy's theorem tells us that a Brownian motion can be approximated by a random walk. In the sense of weak convergence. Okay. So in dimension 1, we take the following setting. So we assume that we take IID random variables, independent and identically distributed random variables, okay, such that the expected value of yi is equal to 0, okay, and we can assume that the variance of yi is equal to sigma square. Okay, this is different from 0. So everybody is familiar with this notation: independent, identically distributed random variables. Okay, and then we define the random walk associated to these random variables as the sum from k equals 0 to m of yk for m bigger or equal than 0. Okay? And then we construct a sequence of processes xt n as being the random walk at the position at the integer part of t plus an interpolation t minus integer part of t of y of integer part of t plus 1. And this for t between 0 and n. Okay? So we just make continuous in this way the random walk. Okay? So we take a random walk and we construct a new process, a process that has continuous paths, okay, which is an interpolation of the random walk. And then we normalize this process. Okay, so we take xt, oh, this is tilde, I use tilde in notes. Xt n will be 1 over sigma square root of n x tilde n time nt. Okay, so this is 1 over sigma square root of n s nt plus nt minus nt divided by sigma square root of n y nt plus 1 for t between 0 and 1. Okay? And Dosker theorem tells us that x and t converges as n goes to infinity to a Brownian motion, this for t between 0 and 1, and this convergence holds in the sense of finite dimensional distributions, okay, and also in the sense of Skorokhov topology. Okay. Proving the finite dimensional convergence of the process is quite an easy example, I will say. It's just a consequence of the central limit theorem, okay, and the Markov property, okay. And from here, it's easy to check that the process B should have independent and stationary increments, okay. But most important for us here is that Brownian motion has the scaling property, which is that for every C strictly positive, the process C times B C minus 2 T for T bigger or equal than 0, given that B0 is equal to x. Okay, so the process change of a scale of time in this way and a space of and a scale of a space in this form, starting from x. This one has the same law as the process without any change of a scale of time or space, but just starting at c times x, and this happens for every x in R. Okay? And this is something, this scaling property is something we can easily observe from this construction. Okay? So if we plug here C2, C minus 2 and C times here, okay, what we will get is again a Brownian motion, okay, but just starting at a different point, okay? So that is an easy exercise. Check the scaling property from the limit. Okay? And this is perhaps the first example of an scaling limit, one of the most popular examples of an scaling limit. Okay? And then there are a lot of many others. So I'm gonna write three more examples. Okay. Are there any questions with respect to this example? Well, in fact, there is no need at all to restrict t between 0 and n. You can take any t, in fact. There will be no problem. Okay? Just here we will take 0 infinity. Okay? And the convergence is true in any, still for that process. Okay? That's not a problem. But I wanted to remark that because you're going to need that when you check the scaling property from the limit. Okay. At any moment, if there is a question, please just stop me, just ask. Okay. Example 2. That is coming from extremal processes. Okay. So here again, we take yi independent and identically distributed random variables such that yi are positive, okay? And we will assume that the distribution of y is heavy tail. By that I mean that there exists an index alpha strictly positive and L and slowly function L such that f bar of x, which is 1 minus f of x, which is just the probability of y1 being bigger than x, can be written as x to the minus alpha L of x, okay? And L is such that for every c strictly positive, L at c times x divided by L of x converges to 1 as x goes to infinity. Okay? This is what is called a slowly varying function. Okay? Okay, so we have IID random variables yi that are non-negative, okay, and whose tail is heavy. Okay. And then we take the maximum of these random variables. Okay. So we define mk to be the maximum of the first n random variables and take the process xn t to be mn t, the integer part, if t is bigger than or equal than 1 over n, and then I will divide this by a sequence an, and x1 divided by an if t is smaller than 1 over n. Okay, and this an will be the generalized inverse, the infimum of s bigger than 0, such that f bar of s is smaller than 1 over n. Okay? And here it is important to notice that by this construction, f bar of an behaves like 1 over n as n goes to infinity. Okay? This process x and t was in fact first studied by Lamperti in the 60s, and later by Resnick, I think in the 80s. Okay, and what they prove is that x n t converges as n goes to infinity to a process xt. Okay, this convergence holds in the sense of finite dimensional distributions and in the sense of Skorhod topology, so in the weak sense, okay, or in low, and X is a process whose finite dimensional distributions are given by the following expression. I should maybe move there. Yeah. So the finite dimensional distributions of that limit process are such that for every T1 is more equal than T2 is more equal than Tn infinite and maybe k x1, x2, xk in 0 infinity, the probability that xt1 to xtk is more or equal than xk is given by g to the power t1 of x tilde 1, g to the power t2 minus t1 of x tilde 2, g to the power tk minus tk minus 1 at xk tilde, where g of x is the exponential of minus x to the minus alpha for x bigger than 0, okay, and x tilde 1 will be the smaller of the xi's x tilde 2 is the second smallest xi, okay, and in general x tilde j is the infimum for I equal j of 2k of xi. Okay. Okay. How do we prove such a theorem? Well, in fact, I will just explain how to prove the one-dimensional convergence. We can also check the two-dimensional convergence, but I will not do the Skorohod convergence. Okay. Yes, it's a power. So yeah, so g t of x is exponential of minus t x to the minus alpha. Yeah. Okay. Yeah. Okay. Just before explaining the proof of this, we can just check that x also has the scaling property for all c strictly positive. So we have that c to the minus alpha t positive times c has the same law as xt for t bigger or equal than 0. Okay. Alpha is the same alpha as this one here. Okay, and we can easily check this claim by just plugging the expressions here. Okay? So that again can be seen as an exercise, as a basic exercise. So use this expression for the finite dimensional distributions, okay, to check that that the process that we have here has the same law as the process on the right. Okay? That is very easy to check because of the form of the function g. Okay. So we started at 1:15, and we finished at 2:25. The first lecture, or just to know. Or to is that? Yeah? Okay. It's just, so I still have 40 minutes for the first lecture. Okay, that's fine. Okay, so let me explain the one-dimensional convergence. So take t positive, and take the probability that xn t is smaller or equal than x. Okay. Remember, this is just the probability that the first nt random variables are smaller or equal than xan. Okay? But this is just saying that x1, no, y1, it's not x, it's y. y1 is smaller or equal than xan, etc. y and t is smaller or equal than xan. Okay? Because it's the maximum is smaller or equal than a quantity. That happens if and only if all of the random variables are smaller or equal than that quantity. Okay? But remember, these random variables are all independent and identically distributed. So this is just the probability that y1 is smaller than xan to the power nt. Okay? So this is equal to 1 minus f bar of xan to the power nt. But remember the expression of f bar of x is equal to x to the minus alpha L of x. So this can be written as one minus x an to the minus alpha L of an x to the n and nt divided by n. Okay, but here, yes, I'm going to write this as 1 minus x to the minus alpha an to the minus alpha L an times L an x divided by L an, and then n nt divided by n. Okay, but this guy that we have here is just f bar of an. Okay, and remember, by definition of Ln, this is just like 1 over n. Okay, and by the properties of slowly varying functions, this is just like 1. Okay, and this guy here is going to t. Okay, as n goes to infinity. Okay, so this is behaving like 1 minus x to the minus alpha divided by n t. Okay, and this, as n goes to infinity, is just like exponential to the minus x to the minus alpha t. Okay, and this is just g of x to the power t. G, t, we cannot read it. Okay, so this is just like g x to the power t. This is all as n goes to infinity. Okay? Is there any question about that? Is that okay? Okay. Well, how do we prove the two-dimensional convergence? I will not do all of them, of course, but just two-dimensional. So we have the probability that xn t1 is smaller or equal than x1, and xn t2 is smaller or equal than x2. Okay. So this can just be written as the probability of xn t1 being smaller or equal than x1 times the probability that xn t2 is smaller or equal than x2 given the first. And I think here I need to assume that x1 is smaller than x2. Okay? If that doesn't happen, I can just take the smaller of them. Okay? So we know this guy converges. Okay? And what happens with this one? This one, in fact, well, we can leave the first one as it is. And the second one is just the probability that yj is smaller or equal than x2 an, and this it happens for n t1 is more equal than j is more or equal than n t2, okay, and I is smaller or equal than x1 an, and this for 1I n t1. Okay? And this divided by the same probability. Okay. Okay, so by this conditioning, I'm forcing these random variables to be below this one. Okay, and if I want that the other ones are that the whole of them are below x2, okay, what I need is that because this x1 is smaller than x2, what I need is that the remaining random variables are below x2 times an. Okay, because x1 is smaller than x2. Okay, but this is very convenient because the random variables that are here are independent of the random variables that are here. Okay, so this event will cancel this event that is here. Okay, and then I will just need to study the remaining random variables that are here. So this is equal to the same, to this term that is here. And then this one, which becomes just the probability that yj is smaller than x2 an for j in nt1, this is open, and nt2. Okay. So this is just essentially the same as taking, because these random variables now they are IID. Okay. So it just depends on the number of random variables that fit in this interval. Okay. So this is times the probability that yi is smaller than x2 an for I in 0 n t2 minus n t1. I guess this is close here. So now, this is very convenient because it looks just as this one that I have here. Okay? I just need to change here nt by n t2 minus n t1. So change nt by this. So remember, this is just the number of random variables I am considering in this expression. Okay? So now the number of random variables that I am considering in this expression is around nt2 minus nt1. Okay? Is that clear? Okay, so I can make the same calculation as I did here, and I will get that this is behaving as n goes to infinity as g t1 x1 times g t2 minus t1 in x2. Okay, so if you want to do the same for k random variables, for k times, you just need to split in k blocks of random variables. Okay? Here we split in the 2 blocks that appear in this probability here. Okay? Well, at those times, in the times where this was done, there were many others. There were many other examples. So in the 60s, there are many other examples. For instance, in renewal theory, in the theory of branching processes, and in many other areas. Okay? And all of them share the property, the scaling property. And that is a fact that Lamperti noticed. In a paper in I think in 62. Okay. his main result characterizes self-similar processes as the class of processes that may appear as scaling limits. So to state that theorem, let me just give a definition. So let x t be a stochastic process defined on a filtered space omega ft is the filtration, and px for x in Rd. Okay, so the laws of the process is starting from little x. This process is taking values in Rd. We will say that x is self-similar if there exists an index alpha, possibly real, okay, such that for all C strictly positive, the law of the process C times x t C to the minus alpha for t positive starting with x is equal to the law of the process without any change of scale of time or space, but just starting at c times x. Okay? And by this I mean that the finite dimensional distributions of the processes are the same. Okay, just as we saw in the previous examples. Okay? And in this case, if alpha is not 0, we will say that x is 1 over alpha self-similar. Examples of this are, of course, the Brownian motion, the extremal process I described in example, stable processes, but many others. So Brownian motion is 1/2 self-similar. The extremal process in the example. Okay, this is 1 over alpha self-similar. Alpha is determined by the tail of f. But there are also Bessel processes which are 1/2 self-similar of any dimension. Okay. There are stable processes. So alpha stable processes, they are 1 over alpha self-similar. Okay. But there are other examples like fractional Brownian motion, fractional stable processes, and so on. Okay. The examples that we have here, the first 4 examples, they all have the Markov property. They are Markov processes. Okay, and these are the class of processes that will be of interest for us in this course. But of course, there are many other self-similar processes with independent increments, with stationary increments, with no Markov property, and so on. Okay, but I will not focus on that. On those processes, I will mainly focus on Markov processes. Okay, but still, the theorem that I will write now is true for any self-similar process. So Lamperti's main theorem let's say the following. So take yt be a stochastic process in Rd, okay, and f a function from R into R such that f is measurable and f is not 0, okay, f is not equal to 0, so it doesn't take the value 0, and define a new process, yc, by the relation yc at time t is just the process y at time t times c divided by f of psi as t for t positive. Okay? So we just take the process y at a different scale of time. So we make a dilation of time. And then we make a dilation of a space by f. Okay? Okay. So the claim or the statement of the theorem is that if yc has a non-degenerate process x as limit as c goes to infinity, okay, in the sense of finite dimensional distributions. Okay. So that means that the random vector yc t1 yc tk or tn converges in law as n goes to infinity, as c goes to infinity, to the vector xt of the law of xt1 up to xtn. Okay? And x is not degenerate in the sense that it's not equal to 0 everywhere. Okay? Then x is a self-similar Markov process, not Markov process, it's a self-similar process okay. Mm-hmm. With index alpha in R for some alpha, okay. And f is a regularly varying function at infinity with index alpha, the same alpha as in here. Okay, that means that f of c is equal to c to the alpha L of c, with L slowly varying. Okay. And yeah. We have that any, furthermore, we have that any self-similar Markov process not Markov, any self-similar process can be obtained in this way. Okay. So that so what Lamperti observed is that it was more than a coincidence that the process that were obtained as a scaling limit had the scaling property. Okay. Those times, of course, the word scaling was not there, but so this is it. So he proved that if we have a process for which we can modify the scale of time and the space in this form and get a process that is not degenerate, then the limit process is self-similar, okay? and in fact that every self-similar process can be obtained in this form. Okay? So self-similar processes is the totality of processes that can be obtained by scaling limits. Okay? So that is the main interest of self-similar processes. Okay? That's why I think, well, this is one of the reasons why these processes are so important and so useful in applications. Okay? I will not give the proof of the result. You can check Lamperti's original paper, and in fact, the proof is not very difficult. It uses mainly the theorem of types of Lamperti. And that theorem states that if we have a sequence Gn and F1 and F2 distributions, okay, so we have a sequence of distributions and two distributions F1 and F2, okay, and sequences AN and alpha n such that Gn of an x converges as n goes to infinity towards f1 of x, and Gn of alpha n of x converges as n goes to infinity towards f2 of x for every x continuity point of f1 and f2, okay, then the limit of the quotient an over alpha n as n goes to infinity exists and is strictly positive and finite, and yeah, and f1 and f2 are related by this limit. Okay? Yeah, that's it. Okay? So necessarily, so if we have two normalizing sequences for Gn, okay, those normalizing sequences should be equivalent in the infinite, at infinity. That is something that one can expect. Okay? But that is used in the proof of the theorem in order to prove the scaling property. Okay? That's an easy example. That's an easy exercise that you can try. Let's say this is a medium size, medium complicated exercise. Okay? So check that that if check that x should have the scaling property at least for dimension 1, and that f is regularly varying. Okay? And for checking that f is regularly varying, it is enough to check that for every c strictly positive, the limit of f c times t divided by f of c, sorry, not t, c, as c goes to infinity, is in between 0 and infinity. Okay? So assume that this convergence holds, okay, for a fixed t, okay, and use the theorem of types of Lamperti to check that there is a scaling property and that f should be regularly varying. Okay. Okay. Let me see. Should we make a break now? Yeah, let's make a break now. Are there any questions or comments? Yeah.
The theorem of Lamperti.
Yeah.
In order for x to have Markov property, what is necessary?
Well, if y has the Markov property, I will say that x will have the Markov property, but it's not necessarily sufficient. I mean, y may not have the Markov property, okay, but it may get it as in the limit. Yeah. 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 Thank you.